Good evening, Herefordshire. Yes, this is the beginning of everything, and as you can see from the subtitle there, I'm going to try and describe the origin and the very early history of the universe. I'm going to do that in somewhat less than an hour. Compared to the end of everything, which spanned, of course, many trillions upon trillions of years, the story of the beginning of the universe is essentially over in 3 minutes. So it's going to take me longer to describe than the actual event itself. If we look out into the universe, here's a sky survey. It looks a little bit like a CGI, it looks like a simulation, but think of this more as a 3D atlas. We have mapped out many millions of galaxies in terms of their position on the sky and their distance. And that's been converted into this 3D atlas. And we're now, as it were, flying through this atlas. So we can see the universe is full of galaxies. But those galaxies aren't uniformly spread out. They're bunched together. And occasionally we can see that bunching. Sometimes we see groups of galaxies, clusters, or sometimes superclusters of galaxies. And the more we look, the more we see structure. We see lines of galaxies in filaments. You can see one in the background there. So they're not uniformly spread. They're bunched together into filaments, into a web-like structure, and there are some regions of the universe that appear to be almost empty, voids of galaxies. So the question is, when we look out into the universe and we see all of this, billions of galaxies that contain billions of stars, where did all this stuff come from? That's the question we're essentially trying to address. Now we know that pictures like this, the Hubble Deep Field, show us there's an awful lot out there. This of course is only a tiny patch of sky. There might be a few thousand galaxies in this particular image, but because this is only a tiny patch of sky, we can extrapolate upwards and we deduce that the observable universe must be full of many hundreds of billions, perhaps even a few trillion galaxies. And if those galaxies are anything like the Milky Way, we know they contain probably hundreds of billions of stars. So we know there's a huge number of stars and there's a lot of gas and a lot of dust occupying the observable universe. But what about the origin? This is what I'm talking about, the creation of everything we can see in the universe around us. When did it happen? Well, it happened approximately 13.8 billion years ago, as best we can tell. All of this, of course, is subject to our current understanding of how the universe began and how it's evolved into the universe that we see today. But our best calculation so far is that the universe is 13.8 billion years old. How long did it take to make the universe? Well, as we will see in a few slides' time, it took approximately 3 minutes to make the universe. Where did it happen is a question that often crops up, but we have to remind ourselves we're talking about the beginning of everything, and therefore it happened everywhere. It didn't happen at one point in space. We can't look to a particular point in space and say, is that where it happened? No, it happened everywhere. Why did it evolve the way it did from its creation 13.8 billion years ago to what we see today? Well, we believe it evolved the way it did because of the laws of physics. Or if you want to turn that around, the laws of physics are our understanding of how the universe came to look the way it does. How do we know all this? Well, same answer. We know all this because of the laws of physics and our assumption that the laws of physics hold. In other words, nothing is outside the laws of physics. So you can liken the problem to trying to understand the rules of the game, such as a game of chess. If we look at a game of chess like this, a snapshot of a game that looks like it's at the end of the game, can we figure out from a picture like this what the rules of chess are? And the answer, of course, is, well, that's rather tricky. We look at a picture like this and we see lots of shapes that we don't understand. There appear to be two colours involved, so maybe there were two players in this particular game. But if we didn't already know the rules of chess, it would be rather tricky to work out what's going on here. And the same is true if we look at, for instance, a picture of another galaxy. This one is relatively close to us, and so a Hubble Space Telescope image of this galaxy shows a huge amount of detail. But it's still a snapshot. We can't sit and watch it evolve, because it would take hundreds of millions of years to rotate, and it would probably take billions of years to evolve. It would be nice if we could watch it in progress, in much the same way that with a game of chess, it would be nice not to take a snapshot of a game of chess, but to watch people playing. If we could have a video of a chess game in progress, then we would stand a chance of understanding what the rules of the game are. But just as for a single galaxy, all we have is a snapshot and we can't watch the galaxy evolve, we can ask ourselves, well, if we can't watch a video of a chess game, could we photograph not one chess game, but could we photograph 1,000,000 chess games all at different stages of the progression of the game? Or could we snapshot 1,000,000,000 different games in progress? If we could, then even though we wouldn't be able to watch any individual game, we might still get an idea of the rules of the game by looking at how the board is arranged in 1,000,000,000 different examples. And it's the same sort of idea with the universe. Watching one galaxy doesn't really help us. But if we take enough snapshots of lots of galaxies, we can't watch them evolve, but these galaxies, only a few thousand in this image, and of course it doesn't matter if we take a Hubble image or whether we take a James Webb Space Telescope image, we're still imaging thousands of galaxies. They're still snapshots, but because of the finite speed of light, the more distant galaxies, we're looking at them as they were in the past. So in a sense, we have frames of a video in that we can look at galaxies close to us as they are now, and we could look at more distant galaxies to see how they were in the past. So we can't watch evolution, but we can get pretty close by taking enough snapshots. But even if we don't look out into the far universe, if we look very locally and say, how is our Milky Way put together? We look at the stars around us and everything looks enormously complex. How can we possibly understand how a structure like this, a whole load of light and dark nebula of different colours and a whole load of stars of different colours, perhaps you recognise the horse head in the bottom left and the great nebula in Orion just off the top right of this particular image. It is so complex, surely the rules must be so complex. Do we really have a chance of understanding the rules of the game, the laws that dictate how the universe came to look like the way it does? Well, one thing we have to remember is that just because something is complex doesn't necessarily mean it's incomprehensible. Here's a mathematical collection of pixels. So it's not a universe as such, but you could argue that in the abstract sense it is. It is a very complex collection of coloured pixels, and it's been generated by a rule, a law if you like, or in this case a mathematical formula. We can zoom into any part of this and we see more and more and more detail. But a single rule, a single formula is able to generate every pixel, not just the pixels we're looking at, and we might only be looking at perhaps 1,000,000 pixels in this particular image. But we could in principle zoom in billions of times and still see more and more and more detail. You look at some of the detail here and you think, well, does it actually repeat? Because some of these motifs look very similar. Well, they are similar, but no, they never actually repeat. Every structure, every little swirl that you see here is distinct from every other swirl, in much the same way that every star in the galaxy might be similar to some of the other stars in the galaxy, but no two stars are the same. Similarly, no two features, no two motifs, no two swirls in this particular mathematical set of pixels ever reproduces. So if we have trillions upon trillions of pixels in this mathematical set, how complex is the formula that is capable of producing each and every pixel in this collection? It's that. Z equals Z squared plus C is all you need to generate an enormously complex, you could argue infinitely complex collection of pixels. So we come back to one of my favourite quotes of Einstein. Complexity and incomprehensibility are not the same thing. And you could argue, he does, the most incomprehensible thing about the world, and in this context we can take world as meaning universe, the most incomprehensible thing about the universe is the fact that it is actually comprehensible. Just because it appears to be enormous on a human scale, just because the length of time the universe has existed and possibly will exist into the future is unimaginable, that doesn't mean we can't comprehend how it came into existence, how it ended up the way it is now, and what might happen to it in the future. There's no particular reason why the universe has to be comprehensible to a particular species of monkey who came out of the trees a few 100,000 or a few million years ago. And yet, apparently, it is. So here's the flow of thought that these Homo sapiens, these monkeys that fell out of the trees, have actually put together in decades past. We've made observations, and we have observed over the last 100 years or so that galaxies appear to be moving away from each other. They all appear to be moving away from us, but that's just, as it were, an accident of perspective. No matter where we were in the universe, we think all galaxies are moving away from each other. That's an observation. So we come to the conclusion that the universe is expanding. We can also make other observations much closer to home. We can do experiments here on Earth that tell us how matter is put together, what atoms are made of, what neutrons and protons and electrons are doing to make up us and everything else we see around us. And we can do experiments in particle accelerators like the Large Hadron Collider, for instance, that gives us a better understanding of the building blocks of matter. And as far as we can tell, the building blocks that we see here on Earth presumably must be the same as the building blocks everywhere else. But we do have to make some assumptions. If we can understand the laws of physics that dictate how things behave on Earth, we have to assume that the laws of physics here are the same as the laws of physics anywhere else. If that wasn't true, that the laws of physics as we measure them in the United Kingdom are different from the laws of physics in Australia, or the laws of physics in Alpha Centauri, or the laws of physics in the Andromeda Galaxy, if they changed from place to place, we would have no chance whatsoever of understanding how the universe is structured. Similarly, we have to make the assumption that the laws of physics that we measure and attempt to understand now are the same as the laws of physics used to be and the same as the laws of physics will be in the future. Again, if we don't make that assumption, if we assume that the laws of physics can change from one day to the next, then anything we learn today does not tell us what happened yesterday and does not allow us to predict what's going to happen tomorrow. So we have to make this assumption that the laws of physics are immutable, simply because if we do not make that assumption, if we assume that they change depending on where we are, and they change depending on when we are, then we have no chance of understanding anything, ever. So those assumptions are necessary. If we put the observations together with those assumptions, we come to the conclusion that the universe was created in a hot, dense state 13.8 billion years ago and has been expanding and cooling ever since. We come up with that 13.8 billion years by combining our observation of what the universe is doing now with our understanding of how matter behaves. So the big question is, where did everything we see come from? When we look out into the universe, the observable universe is a sphere some 100 billion light years or so in diameter. And it seems to be full of trillions of galaxies which contain hundreds of billions of stars and huge amounts of gas and dust and other stuff. Where did all that stuff come from? We can ask ourselves how far back in time, if we think the universe is 13.8 billion years old, how far back can we go before we say really, we are not altogether convinced we really understand what's going on. Can we go back to the first year of the 13.8 billion year history of the universe? Yep, no problem with that. Can we go back to the first day? Yes, I know day is a concept that depends on the Earth's rotation, but you know what I mean. Can we go back to the first day after the start of creation and say that we think we understand what was happening? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second after the universe was born? Do we think we understand what was happening? Yes. What about the first millisecond? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No, not really. The first 1/1,000,000th of a second is a sort of a watershed moment. Before that first 1/1,000,000th of a second, before that first picosecond, we are on somewhat shaky ground. Everything after that point is relatively well understood. Notice the word relatively there. In other words, we think we've got a good handle on what happened after the Big Bang from 1 picosecond onwards, up to the present day and hopefully into the future. We can't, in all honesty, say we understand what was going on in that first 1 picosecond. Why is that a watershed time? I'll come back to that in just a couple of slides' time. So that was a very long introduction to what it is that I'm trying to talk about this evening. I'm going to show one slide covering a few basic ideas, some of which you're already familiar with, perhaps a few others you won't be, but we'll need to get that established to make sure we can make sense of what's coming next. Then I'll be describing what happens in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes, and to avoid being here for the rest of eternity, I'm then going to change the gear somewhat and accelerate through the next 380,000 years. We're going to move fast forward to that particular point. That wasn't chosen at random. There's a particular reason for choosing that time point. And then we'll jump again 13.8 billion years to the present. So that's what we're going to be doing. So firstly, a few basic ideas are necessary. Now, the first one, I hope, comes as no surprise to any of you. We are made of atoms, and indeed a lot of the universe is made of atoms as well. Atoms are made up of a positively charged nucleus and a whole load of electrons buzzing around it. Now, that means an atom is a compound particle. You can think of it as a particle, but it's a particle that's made of other stuff. We can take that atom, and we figured out a little while ago what the atom is made of, and we figured out how we can separate an atom into its constituents. It's made of a nucleus and a whole load of negatively charged electrons buzzing around it. As best we can tell, the electrons are fundamental particles. In other words, they are not made of anything else. An electron just is. You can't take an electron, cut it in half, have a look inside and say what's in the guts of an electron. As far as we can tell, you can't do that. But a nucleus is different. A nucleus, again, is a compound particle. It is made of something else. We can take a nucleus and we can look inside. And we found quite a few decades ago that a nucleus of an atom is made up of different particles which we label protons and neutrons. Neither of those is fundamental either. And if I take the proton as an example, protons are made of more fundamental particles which are called quarks. We don't have to worry about why particles have these particular names, quarks or protons or neutrons. We're just going to use these as labels for particular building blocks which allow us to put quarks together to make protons. Protons and neutrons make a nucleus plus electrons make atoms. Atoms make molecules. Molecules make us and most of the world we see around us. There's an implied energy scale here because it takes a certain amount of energy to take an atom and to rip it apart into its constituent parts of nuclei and electrons. And it takes more energy to take a nucleus and separate it into protons and neutrons. And it takes more energy to take a proton and attempt to separate it into its constituent parts. So there's an energy scale from low to high in this sort of picture, this sort of Russian doll picture of how the universe is put together. But remember what we said about the universe. The evidence is that the universe was made in a hot, dense state and ever since has been expanding and cooling. So if low energy is at the top and high energy is at the bottom, to a physicist, high energy means high temperature. Temperature, if you like, is just a way of measuring the average energy of all of the particles in the system that we are considering. So low energy and high energy correspond to low temperature and high temperature. But the universe was born hot and is cooling down. So again, there's an implied time scale going from hot to cold that runs from the bottom upwards, because high energy at the bottom corresponds to hot, low energy at the top corresponds to cold. So that means if the universe was made hot, if we start with a few fundamental particles, for instance, if we somehow generate a few quarks and we want to make a proton in this Russian doll model, we can't simply put quarks together to make a proton because the universe is too hot. The quarks will have so much energy they simply won't stay together as a proton. We have to wait until the universe has cooled off a little bit before it's cold enough for quarks to get together to make protons. And we have to wait even longer for the universe to cool off even more before protons and neutrons can get together to make the nuclei of atoms. If we try and get protons and neutrons together before this particular time has been reached, the universe is too hot and protons and neutrons have got too much energy and will not get together into a nucleus. And similarly, a nucleus and electrons in principle can get together to make atoms, but not until the universe has cooled off even more, because otherwise the nucleus and the electrons will have too much energy and they will simply rip the atom apart if you try and get them together before the universe has had time to cool off to the relevant temperature. So that's the basic idea of how the universe was made, from the bottom upwards. So let's have a think about where we should start. T equals 0, time equals 0. Perhaps there's no surprise when we ask the question, what happened at the instant of t equals 0? The answer is, we don't know. Science cannot at present provide any definitive answer to what actually happened at t equals 0. Now, there's plenty of hypotheses. A hypothesis is simply a conjecture that can't be proved at the moment. A lot of people seem to think, well, maybe energy was borrowed from nothing. A quantum fluctuation, that sounds like a cheat, and it sounds really weird that you can borrow energy from nothing. Yes, it does sound weird, but quantum mechanics is weird. Quantum mechanics has been with us for 100 years now, since the 1920s, 1930s. And so far, nothing has shown that it is incorrect. So we have a quantum theory which tells us it's perfectly okay to borrow energy from nothing. And remember, Einstein has told us that E equals mc squared. In other words, if you have a certain amount of energy, you can make matter. And if you have a certain amount of matter, you can convert it into energy. So to all intents and purposes, energy and matter are interchangeable as far as this exchange rate is concerned. And according to quantum theory, it is possible, a so-called quantum fluctuation, to borrow energy from nothing. And if you borrow energy from nothing, you can then use that energy to make stuff. Now, yeah, I know that sounds like a cheat. If you want a 4-year course on quantum mechanics, I'll gladly give you that, but that's outside the scope of this particular talk this evening. How much can you borrow, and for how long? Well, it's pretty much like taking a loan out of a bank. You could, in principle, borrow a lot, or you can borrow a certain amount for a long time. The amount of interest you have to pay depends on the product of how much you borrow and for how long. You can borrow a lot for a short length of time to keep the interest low, or you can borrow a little bit for an extended period of time to keep the interest low. According to quantum theory, the amount you're allowed to borrow from nothing has got an upper limit. You can borrow a lot of energy for a short time or vice versa. So one of the key questions is, well, if this is the answer to how the universe came into existence by borrowing from nothing, what matters is how much energy did we need to borrow before the universe noticed and we had to pay back the loan? Well, when we look out into the universe, we can make an estimate of the total energy of the universe. We can look at all of the matter that's out there and convert that to energy through E equals mc squared. And we can look at all the gravitational energy. Gravitational energy is negative, mass energy is positive. When we add it all up, what do we find? The total energy of the universe looks like it might be close to zero. And if it is zero, the time period we've got to repay the loan might be infinite. Again, all of this is rather speculative. This is purely hypothesis. We have nothing to prove that this is in fact the case. But a lot of people, a lot of scientists, a lot of theorists believe that this might be the way the universe came into existence. Let's move on from t equals 0 to a time of 0.00, you can count the zeros yourself, a very short length of time after the universe came into existence. 10 to the minus 35 seconds after its creation, the universe has expanded until it's the size of a golf ball. And by the universe, I'm talking about the observable universe. We have no idea what's happening outside our observable universe. At the moment, the observable universe is a sphere 100 billion light years in diameter, approximately. Everything that is currently inside that sphere of 100 billion light years diameter used to be a lot closer together. If we wind the clock back far enough to this point in time, then everything in the observable universe used to be separated by centimeters rather than light years or millions of light years or billions of light years. Now, it staggers the imagination. I don't think anybody has the imagination to try and think about how that could be. Nobody can imagine the entire observable universe into something the size of a golf ball. But our current theories imply, the Big Bang theory implies that at some state in the past, this presumably was the case. I like this analogy of a golf ball because not only does it put everything in the observable universe a few centimeters apart, but just like a golf ball, the universe is not perfectly smooth. It has dimples, just like a golf ball. Now, they're not dimples in the surface, they are variations in density and temperature throughout the universe. But by analogy, we can say a golf ball isn't perfect either. It's not a perfect sphere. It has small variations, okay, on the surface rather than in the body of the golf ball, but that's as close an analogy as we can get. And those variations, those tiny fluctuations in density and temperature within the golf ball, eventually, when the universe has expanded and the golf ball becomes much, 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 much bigger, those variations in density will ultimately become the large-scale structures across the universe. In other words, they will end up, the densest parts will end up as stars and galaxies, and the least dense parts will end up as the voids between intergalactic space. Let's jump forward now to 1 picosecond, 1 trillionth of a second, 10 to the minus 12 seconds into the future. The universe has now expanded from the size of a golf ball to something about the size of the solar system. Yes, of course, the solar system doesn't exist yet, but this is just trying to give us a handle on the measurements we're talking about. So clearly, if we go from something the size of a golf ball to something the size of the solar system in a tiny fraction of a second, then of course that means space has expanded much, 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 much faster than the speed of light. And that is perfectly okay. Einstein tells us about how things can behave and how objects can move through space, but that doesn't put any restriction on how fast space can expand. And indeed, there are parts of space which are even today expanding faster than light. The temperature at this point, 1 picosecond, has fallen to about 10 to the 15 Kelvin. And the energy of each of the constituents in this soup of particles, I'm calling it a quark soup. I'm assuming that we've borrowed some energy from nothing and we're using that energy to make stuff. It's a soup of quarks and other particles. It's probably made up of quarks and electrons and other things as well, but just for simplicity, I'm just going to call it a soup of quarks. So each of the particles, each of the things in this quark soup, the energy of each of these particles at this temperature of 10 to the 15 Kelvin is approximately equal to the energy that we can reproduce in the Large Hadron Collider. In other words, we can generate particles with these sorts of energies and bang them into each other and see what happens and start to understand what must have it been like at the particular point we're talking about here, 1 picosecond, at a temperature of 10 to the 15 Kelvin. And it's precisely because we can reproduce these energies and we can test our ideas in a particle accelerator. That's why this is the watershed time. From this point onward, the average energy of all the particles in the universe are less than the energies that we can reproduce in the Large Hadron Collider, and therefore we can test any idea we have about how we think things have been behaving. From this point onwards, we can test our ideas, and that, of course, is the core of science. Any theory produces predictions which must then be testable. Prior to this point, the energies were so high, we have no way of reproducing them. This point onwards, we can reproduce the energies, we can test our ideas. Matter and antimatter are continually changing backwards and forwards. Energy makes matter and antimatter, antimatter and matter can make energy. Whenever energy makes matter, it must also make an equal amount of antimatter. That's how we think it always works. If we want to make an electron, we make an anti-electron as well. If we want to make a quark, we make an anti-quark as well. Antimatter is just the opposite of matter in the sense of it's a particle with all of the same characteristics, all of the same properties, except the electrical charge is switched. So the antimatter equivalent of a negatively charged electron is a positively charged anti-electron, or a positron as we call it. And matter and antimatter are made in equal amounts. In other words, if we take a certain amount of energy, I don't know how to represent energy in a PowerPoint presentation, so I'm just going to label it as a big capital E. That's a certain amount of energy. And that energy can make matter and antimatter particles. Which ones? Really doesn't matter. It could make, okay, probably not an orange and an anti-orange. It could make a quark and an anti-quark. It could make an electron and an anti-electron. The point is, it doesn't actually matter which particular particles are being made here. If you make a particle of matter and antimatter, very soon after you make them, they will annihilate and produce energy again. That energy can then go on to make another particle of matter and antimatter. Not necessarily the same ones again, it might make something totally different. Probably not a hot dog and an anti-hot dog, that's very unlikely. It'll make some particle and its antiparticle. And that will go backwards and forwards and backwards and forwards. Energy making stuff, stuff making energy, energy making stuff. Backwards and forwards, backwards and forwards. But somehow, in this sort of era, matter gained a very small excess over antimatter. Most of our theories say whenever you make matter, you make the same amount of antimatter. If you take a quantum, a certain amount of energy, you'll make equal amounts of matter and antimatter. But somehow that balance was upset at this sort of time period. Matter gained an excess over antimatter. So what that means is, if you make a certain amount of matter, you don't make quite the same amount of antimatter. I've shown it here graphically as a 10% excess, 1 part in 9-ish, of excess of one over the other. the excess was nowhere near that large. The actual excess was not 1 part in 9, it was 1 part in a billion. So a tiny excess, but a rather important one, because each of the particles we can see here can annihilate with their equivalent to give you energy, and that energy would probably be in the form of radiation, gamma rays. So in other words, electromagnetic waves, light, regardless of which wavelength, let's not worry about that. It's light of one kind or another. But this piece of matter left over, this set of particles, this excess, doesn't have any antimatter to annihilate with. So it can't produce simply radiation. That is left over. So from this point onwards, we seem to be in a universe which is full of electromagnetic waves, i.e. light, and matter, stuff. You and me, and the Earth, and the Sun, and the Milky Way, and the Andromeda Galaxy, and every other galaxy we can see in the observable universe appears to be made of matter. And that is simply the leftover 1 in a billion bits that were left over because of this matter-antimatter asymmetry. We also deduce from this that for every particle of matter, there are a billion photons of light. And that ratio of matter to radiation does appear to be what we see in the universe around us. We're now moving forward to 1 millisecond. Matter and antimatter continuing to pop into and out of existence, back and forth and back and forth. Once the universe has cooled off to this particular point, after 1 millisecond, it is possible for quarks to get together and make protons and neutrons, because protons and neutrons are made from constituent quarks. Remember, up till now, the universe has simply been too hot for those quarks to get together and make protons and neutrons. Now, the word proton and the word neutron are just labels. If we have a bag of 3 quarks that look like the left-hand side, we call that bag of quarks a proton. If quarks get together and they form a bag of 3 quarks that look like the right-hand side, we call that bag of quarks a neutron. I'm not going to go through the details of why they're coloured red, green and blue. I'm not going to go through why they are labelled U or D. All that matters is a particular collection of quarks is called a proton and a different collection of quarks is called a neutron. And if quarks can annihilate with antiquarks and generate energy, which then generates more quarks and antiquarks, then in principle these quarks can change into each other, which means protons can change into neutrons and neutrons can change into protons, because they are simply different combinations of those quarks. Let's go forward to 1 second after the instant of creation. The universe is now approximately 1 billion Kelvin. That might sound really hot, but bear in mind that's not so much hotter than the core of some really big stars. It is now too cold. Only 1 billion Kelvin means that it's too cold for protons and neutrons to readily swap backwards and forwards. We could do that when the universe was hotter, but now the universe has cooled off a bit. It's difficult for protons to change into neutrons and vice versa. Now, protons, which I'm labelling in this particular talk as little red objects, and neutrons, which I'm labelling in this talk as little blue objects, are not the same mass. Protons are a little lighter than neutrons by about 0.1%. In other words, if we were to put them on the scales, we would find the scales go in favour of the neutrons. They're just a little bit heavier. How do we know that neutrons are heavier than protons? We can measure that in the laboratory today. And according to our assumptions about the laws of physics, a proton billions of years ago is essentially the same object as a proton today. Same goes for a neutron. So if neutrons are heavier than protons now, they were heavier than protons 13.8 billion years ago. And if protons are light by about 1 part in 1,000, we can calculate that means that when the universe makes lots of protons and lots of neutrons, the protons will outnumber the neutrons by a particular ratio. It turns out that when you do the calculation, the protons outnumber neutrons in the ratio of 3/4 to 1/4. And I'm just arbitrarily taking 16 particles here to show that 12 of them are protons, the red ones, and 4 of them are neutrons, the blue ones. Why should the universe make more protons than neutrons? Well, it's a fundamental rule that nature always favours the lower energy, or in this case the lower mass, because mass and energy are essentially interchangeable. One way of thinking of it is that if the universe has free rein to make as many protons and neutrons as it likes, well, protons are lighter, so they're easier to make, so it'll make more of them. That's one way of thinking about it. So the full calculations tell us that we would expect this particular ratio. We're now moving from 1 second to a few hundred seconds, in other words, a scale of a few minutes or so. Neutrons are unstable, and some of them will decay into protons. Again, how do we know that? Because we can do the experiments here in the laboratory. We know that if we take a neutron isolated from all of its neighbours, that neutron will spontaneously change into a proton on a time scale of typically 10 to 15 minutes or so. So neutrons will change into protons. It's a fundamental law that we've discovered recently meaning decades. We know that happens, and according to our assumptions about the laws of physics, if it happens now, then we can assume that neutrons in the past would have been unstable and some of them will have decayed into protons. So that means the ratio has changed. Rather than 3/4 to 1/4, in other words 12 red to 4 blue, the ratio of protons to neutrons has now changed because some of the blues have changed to reds. So in this particular picture, 2 of the blues on the right have changed to reds. So now we have 14 protons for every 2 neutrons. And that is sort of frozen in now. The universe is too cold for that to change, because they are now going to start getting together. The universe is now cool enough for them to start getting together. The universe is 100 million Kelvin or so. It is possible for protons and neutrons to bind together. Now they do that in a particular way because we have found that one of the most stable structures that exists between protons and neutrons is this one that I'm holding up. 2 protons and 2 neutrons can get together to form an alpha particle, or if you prefer, the nucleus of a helium atom. So 2 reds and 2 blues will want to marry up and make one of the most stable structures in the universe, an alpha particle, or otherwise known as the nucleus of a helium atom. But you notice that of the numbers we're talking about here, once 2 blues have married up with 2 reds, there are no more blues left. So we're left with 12 bachelors who can't marry up to any neutrons because the neutrons have been absorbed by that alpha particle. So what we're left with is 12 bachelor protons, or if you prefer, nuclei of hydrogen atoms, and 1 nucleus of a helium atom. And that cannot change from here onwards, according to the systems that we've been looking at so far of how particles can change into each other. The universe is now cold, too cold for that to change. After 3 minutes, the relative abundance of hydrogen and helium has been determined, and that is now fixed, or at least it's fixed until a few stars come along and start fusing hydrogen into heavier elements. But that's not going to happen for a little while yet. From this point onwards, for millions and millions and millions of years, the amount of hydrogen and the amount of helium is fixed in this ratio of, in terms of masses, 3/4 hydrogen, 1/4 helium. That is a prediction of Big Bang theory. When we look out into the universe, we can measure what is in the, not interstellar, because interstellar is a little bit too messy. Remember, stars are processing elements. Let's look in between galaxies. where the material is effectively primordial. If we look in between galaxies at intergalactic gas, and we look at that gas and ask what is that gas made of, we find it's 3/4 hydrogen, 1/4 helium. 25% helium, give or take a percent or two. In other words, within experimental observational error, the universe appears to be made of 1/4 helium, just as Big Bang theory would predict if we've understood the physics correctly of how quarks behave, how protons behave, how neutrons behave. So that's one of the reasons that we think Big Bang theory is right, because it makes a prediction which is testable and it gives the right answer. If we want to replace Big Bang theory with something else, then that something else has to produce a prediction of the helium ratio that's equally as precise. We're now going to fast forward. Now that the universe has made all of the hydrogen that we need, we're going to fast forward 380,000 years. Why that particular number? Well, nothing interesting happens for the next 1/3 of a million years. The universe will continue to expand, and as a consequence, the universe will continue to cool down. And it will cool down until this particular point in time, which corresponds to the universe cooling to about 3000 Kelvin. What is so important about 3000 Kelvin? Well, this is the temperature at which atoms get ionized. In other words, if we were to take hydrogen and helium and heat them up to much higher temperatures, we would strip the electrons off these atoms. Turning that argument around, until we get to this point, the universe is too hot for atoms to form. But once we reach a temperature of about 3000 Kelvin, which happens, it has been calculated, at this particular time point, 380,000 years after the Big Bang, at this particular time, the universe is cold enough for atoms to form. In other words, nuclei can hang on to the electrons, and so atoms can exist for the first time in the history of the universe. So the universe changes from being a lot of separate positive and negative ions, positively charged protons and negatively charged electrons that are still floating around in that quark soup. The universe changes from ionized plasma to a collection of neutrally charged atoms. And for the first time in history, the universe becomes transparent. Up till now, any light, and remember there's a lot of radiation pinballing its way around inside this plasma, up till now the light has found it difficult to travel through the plasma. It's been effectively trapped in the plasma because of the positive and negative charges that exist. But now the universe is neutral. It's made up of neutrally charged atoms, it's transparent, and so the light is released. The light can now fly around the universe unimpeded compared to what was happening in the previous 380,000 years. And we see that light today, the light that was released once the universe became transparent. At the time, when the universe was 3000 Kelvin, any object that's at 3000 Kelvin is going to be radiating white hot. There's going to be a huge amount of visible light coming out of this object. And we see that light, but not as visible light, because the universe has expanded in the time since this era that we're talking about. The universe is now 1,000 times larger than it was back here. And if the wavelengths have been stretched 1,000-fold, what do you get if you take visible light, whose wavelength is of order microns? If you stretch it by 1,000-fold, you end up with light whose wavelength is of order millimeters. That's what we call microwaves. So the ghost of the Big Bang is the cosmic microwave background, if you like, the echo of the Big Bang. The light that was released when the universe became transparent is now visible everywhere in the sky as the cosmic microwave background. This is an image of the entire sky unwrapped and laid flat, and it's essentially the same temperature, or if you like, the same intensity, which is equivalent in all directions, but there is a tiny variation. So in this particular map, higher intensity regions are shown in red and lower intensity regions are shown in blue, but they are tiny variations, only tens or hundreds of parts per million. It's only a small variation on a background glow that appears to be coming from all directions. And this mottled effect that we can see, these fluctuations in temperature, which is the same in a sense as fluctuations in density, where did those fluctuations come from? They are, if you like, the result of the dimples in the golf ball. The golf ball that we talked about, the cosmic golf ball in the early slides, the small variations in temperature and density of the early universe. The universe has expanded until it was much, much, much larger, but those small variations are visible in the cosmic microwave background. And that's precisely why a number of people are studying in great detail the cosmic microwave background, the CMB. It's not perfectly smooth. The small variations tell us about those dimples in the golf ball, and trying to simulate how we get from the dimples in the golf ball to the galaxies we see in the sky, computer simulations are able to track that by saying what happens if we were to apply gravitational pull to all of those small variations in density. Can we understand the galaxy structure that we see in the universe around us? So a great deal of attention is being paid to those variations in the cosmic microwave background, because that gives us a handle, it gives us a probe to the very early universe. We can see how those dimples in the golf ball actually give rise to variations in the galaxies we see around us. Remember, the dimples in the golf ball imprint themselves on the cosmic microwave background, and we can run a simulation to see how that results in galaxies. So we can take not the entire universe, but we can take a small chunk of the universe and fill it with matter and imprint a small variation of density and temperature. Perhaps you can see that this particular square isn't perfectly uniform. There's a little mottling in the background because we've introduced a small variation in density in a chunk of the universe here. And we're going to run a simulation. The URL at the bottom of the slide here tells you where you can find more about these simulations. This simulation is going to start with a large chunk of matter and then let gravity do its stuff for a few billion years. And what we see is that gravity is going to grab a hold of some of these denser regions and make them even more dense. So the bright spots that you can see forming are getting denser and denser and denser as gravity is pulling on these dense regions and making them even more dense, which is where stars and galaxies and clusters of galaxies are starting to form, these white blobs that you can see. Notice that this simulation shows that not only do we start to form stars and galaxies, but those galaxies actually aren't uniformly spread throughout the entire simulation. They seem to want to cluster together in these filaments, in this web-like structure. And some regions of the simulation appear to be almost devoid of any white dots, indicating that there are voids where galaxies don't seem to form. Remember the slide with the fly-through that we had early on in the talk? This is pretty much what we actually see. If we map out where galaxies are in our immediate neighbourhood of a few million galaxies around us, we find that those galaxies around us do form this web-like structure. They're not uniformly distributed throughout space. They cluster together, they form filaments, and there are gaps between those filaments. If we were to look at the immediate vicinity of the Milky Way, this is just literally just the local group. There's the Milky Way in the centre, a few small satellite galaxies around it. In the bottom right, there's the Andromeda galaxy, excuse me, and towards the bottom, the Triangulum galaxy. If we were to change scale and ask ourselves what's going on a larger spatial scale, in other words, shrink the local group down to the centre, then we find that there are a number of clusters. We appear to be part of a big Virgo cluster. There's certainly a large Virgo cluster over to the right there. There's a Fornax cluster down in the bottom left, and there are hints of other clusters. Notice that on this scale we can already see that the clusters aren't uniformly spaced around us. They seem to be spread on what appears to be a filament. And if we go again to a larger spatial scale, take all of these clusters and shrink them down and look on a larger scale, we see that the Virgo supercluster, which is just effectively the system that we are part of here, forms a little bit of a filament. And when we look around us, we see other galaxies, we see other clusters of galaxies, other superclusters of galaxies, again, that seem to form in filaments. And there are certain regions where there seem to be very few, not necessarily zero, but very few galaxies. And those voids and this filamentary structure are a direct consequence of the dimples in the golf ball, the small variations in density and temperature that existed in that early cosmic golf ball, that imprinted themselves onto the cosmic microwave background, and ultimately, once gravity had a few billion years to grab a hold of these density fluctuations, gravity managed to pull them together and start to form stars and galaxies. So let's fast forward. What happens in the next 13.8 billion years? Well, we've said that it only takes 3 minutes to make all of the hydrogen. And once we have a universe full of hydrogen, then in principle we can say, well, if we start with hydrogen, well, can't we understand everything? We can certainly say that if we start with hydrogen, we can understand the formation of stars and galaxies. And if we can understand the formation of stars and galaxies, then when stars form, we can start to understand how planets form, and we can understand trees and mountains and snowflakes and rainbows and cats and... Okay, perhaps not cats. I don't think we'll ever understand cats, but we can understand most things. Yes, there are still some details to be worked out. We have to understand some of the details of exactly how we go from a universe full of hydrogen atoms to a universe full of galaxies. Simulations help us understand how one ends up looking like the other. And if we reduce it all, for the sakes of a summary, reduce it all to a rather silly timeline here with the fraction of a second on the left and billions of years on the right, what we've said is that the universe came into an existence at a time we don't really understand. It expanded until it was the size of a golf ball, and if we did borrow energy from nothing, that energy was used to make lots of particles, quarks and electrons. Let's just call it a quark soup, lots of different quarks being made. Once the universe was colder, those quarks could get together to make protons and neutrons. After a few minutes, protons and neutrons could get together to make helium, and all the protons left over are simply hydrogen. If we fast forward to 380,000 years, that means the universe is cold enough for the atomic nuclei to grab hold of the electrons that are also in the soup and make atoms. The universe becomes transparent and the light is released, and we see that as the cosmic microwave background. We're still a little bit in the dark, if you'll excuse the pun, about the dark ages. After the hydrogen was made, we don't know quite how long it took to make stars. If you start with hydrogen and let gravity do its stuff, then it appears that you will make stars and galaxies. But how many millions of years did it take after the hydrogen existed before the first stars were born and the first galaxies started to exist? We know what the galaxies look like now, but when were the first stars and the first galaxies? Presumably in that first billion years or so. But did it take 100 million years, or did it take 200 million years? Well, that's precisely why telescopes like the James Webb Space Telescope are looking back in time to redshifted galaxies that are this sort of age to try and find those first stars and those first galaxies. Then at least we will have an idea of how those hydrogen atoms first formed into stars and galaxies. Simulations tell us it will happen, but we're not absolutely sure of the timescale on which that will happen. We need observations to tell us when those earliest stars formed. And of course, we can't claim that we understand everything. We've taken a lot of the pieces of the jigsaw over the last 100 years or so, thanks to Quantum mechanics, thanks to general relativity, thanks to observations of the universe around us, we've got a pretty good idea of how the universe started and how we ended up where we are now. But there are still some fairly serious questions that are remaining unanswered. Why did matter win over antimatter? In other words, what caused the asymmetry? We know the asymmetry exists because pretty much everything we see on Earth, everything we see in the Milky Way, every galaxy we can see in the observable universe appears to be made of matter, not antimatter. We can make antimatter in the laboratory, we can study it, we can probe its properties, but we still don't understand why the matter-antimatter asymmetry arose in the first place. We don't understand what dark matter is and what it's doing. It seems to be causing the galaxies to rotate at a speed which is not what we would expect by looking at what's all the stars doing, what are all the gas and the dust. In other words, adding up all the luminous matter doesn't seem to account for all the matter that exists. And also, when we look at the expansion of the universe, it seems to have started accelerating in the last few billion years. We attribute that to dark energy, but we don't really understand what dark energy is. So in this talk, I've been talking about the beginning of everything, but I've tried to make it clear that everything in this context means everything that we can see. When we look out into the universe and we see gas and dust and stars and galaxies, we add that all up and we asked, where did that all come from? But everything is not everything that we can see. All the ordinary matter in the universe appears to account for only 5% of the total content of the universe. The other 95%, the dark matter and dark energy, that's still a bit of a mystery. But as they say, that's another story. Thank you for listening.
Thanks very much, Steve. That was wonderful.